Hello and welcome to this final design practice 2 module 40. You may have recalled perhaps that in this particular week we started with an introduction to mechatronics lecture, followed by a lab level demonstration of a very simple process of control of temperature on a small microchip using National Instrument Lab View. The purpose of doing this in this particular course was that you should be aware of some of the tools which are very commonly used for developing a man-machine interface, and that can be translated very well into some of the principles of mechatronics, at least on a prototyping level, on a first hand, maybe the first version level. Obviously, more of embedments and integrability to controllers comes at stage 2, which may really not be in the scope of this particular course. But the idea was to enable you to sort of get to know about how you could interact with real systems, real world systems, by building up an interface through a machine, a computer, and you can rapidly through some programmable logic be able to operate on such a system. So today we will actually continue process ahead of this whole introduction to mechatronics lecture and delve a little more into the aspects of sensors, transducers. I think we had a very good description of sensors while doing the MEMS part of the modules, but this particular illustration would be again sort of a little bit of recap about sensors, but with more focus or emphasis to some real life sensors which are being utilized, more analogous and more again related to the macro world. What we did there was more related to the micro sensors, and then a few slides of this whole idea of intelligent product designing and how it can be integrated with mechatronics. Okay, so let's start this particular module. So we were talking about sensors. So if I looked at some of the definitions as said by the ANSI, the American National Standard Institute, sensor is something, it's a device that provides an usable output, and this output is in response to a specified quantity which can be measured. We call this a measurand. So if this is an analyte, it's a chemical analyte, it gives you some kind of a signal which is transduced into machine readable signal, maybe electrical or optical, and eventually can be digitized or eventually can be made into a readable response through machines. So that's what the standard definition is. Now a sensor may acquire physical quantity and convert it into a signal suitable for processing. Signals could be optical, electrical, mechanical. You learned some things about transduction, which is about this conversion. Now very commonly, because we are talking about computer assistance on one side, and that the enablement of digitizing everything. So therefore it is quite common these days that sensors be integrated to physical phenomena which generates an eventual electrical signal. Okay, so this becomes more integrable to the existing platforms. You could read them, you could work out, measure them, and you could actually give some decisions based on their levels, okay, which would eventually mean the presence or absence of a certain signal. So the active element of a sensor that is there is called a transducer again, which will measure or convert this into the corresponding electrical signal. And what really is a transducer? It basically again converts one form of energy to another. The input to a transducer could be a physical quantity, the output could be like electrical signal, okay, coming out of the sensor. If supposing we are talking about a sensor, typically all the inputs are in the physical domain, the outputs are in the electrical domain, but it could be the other way around as well. If it is an actuator, then basically there is another conversion, that you give it an electrical or maybe an optical signal, and the output is always a physical quantity in terms of a motion, in terms of displacement, relative displacement, so on and so forth. So that's in principle the conversion process of one form into another. A very common example could be, for example, the piezoelectric sensor or the piezoelectric stage, which could be used for a small displacement. So, in the piezoelectric sensor, for example, we could sense a force and produce a voltage. So, if there is a force which is in the shear direction or maybe in the lateral direction, it would produce sort of a response based on the piezo coefficients in these various directions. Alternately, it could be the other way around, that if we provide a voltage signal to a piezo across its two plates, it may result in some kind of a motion. It could be a vibration motion if the signal is alternating current signal, so on and so forth. So, you are producing motion, okay, by at the cost of some energy input, okay, which is in electrical form. So, this again is a piezoelectric. So, in one case this acts as a sensor when a force is converted into a electrical response, and in the second case it acts as an actuator when actually the electrical response is converted into a mechanical parameter. Other examples could be microphone or loudspeakers, which convert the voice of a particular speaker into electrical signals on one end, and in case of a loudspeaker the vice versa, that is the electrical signal which is much more amplified in between to eventually a very loud sound which is audible to a lot of people. So, in one case this guy acts more like a actuator, where the microphone acts as a sensor where typically a set of compression and rarefaction is converted into some displacement of a membrane through which piezo voltage can be generated. The other end, the loudspeaker acts more like a actuator, where there is an electrical signal which is in place and is able to assist the movement of the bass and the tweeter as normally is present in a loudspeaker to create a high level acoustic energy which can be perceived by many. So, I think we have made this definition very clear. Again, if you look about sensing what, and what are the typical detectable phenomena which exist where sensing is needed, there are biological phenomena, chemical, electrical, electromagnetic phenomena, heating, temperature related phenomena, magnetic phenomena. Then there are mechanical motion, for example, displacement, velocity, acceleration, etc. There is optical phenomena, radioactivity. All of them are detectable in the sense that they generate a stimulus which could be actually sensed by a sensor, and a reading output can be deciphered from the sensor, so that based on the output a corrective decision can be taken, be it diagnostics or be it related to motion or magnetic field or even radioactivity, etc. So, the common conversion methods are classified again based on what you are converting as the principal source of the measurand. So, if the measurand is physical in nature, it would cover a lot of domains like thermoelectric, thermoelastic, thermomagnetic, thermooptic, again photoelectric, photoelastic, photomagnetic, electroelastic, magnetoelectric, electromagnetic, so on and so forth. So, these are all where the measurements are physical in nature, okay, and you are converting them into signals which are either magnetic or light based, or again electric in nature. When we talk about chemical sensing, we are typically referring to chemical transport, physical transformations of molecules, talking about electrochemical sensing, so on and so forth, where the measurements happen to be in mostly chemical domains. If the source of the analyte happens to be biological, where the measurement actually is some kind of a biological transformation process or a physical transformation process that we are studying, then the sensor actually falls in the biological sensors domain. So, I think we had very clearly illustrated when we had talked about MEMS, about all these three: physical, chemical and biological sensing systems. So, if we look at commonly measured quantities using some of these sensors, we have acoustic sensors which typically work on measurement of the whole acoustic wave. Wave means amplitude, phase of the wave, polarization aspects of the wave, so on and so forth. It talks about wave velocity, talks about the frequency spectrum. When we talk about biological and chemical stimulus, the commonly measurable quantities are the concentrations of various substances which are either in gaseous or liquid forms. When we talk about electrical stimulus, this could be in terms of a charge, a voltage, some kind of current, electric field. Field could have again amplitude, phase or polarization aspects. You could talk about conductivity, permittivity, so on and so forth. When we again mention magnetic, the quantities that we are measuring is typically the amplitude, phase and polarization of the magnetic field, or the permeability of the material or the medium, or even the magnetic flux sometimes. In case of optical stimulus, we are referring to mostly change in refractive index, reflectivity, absorption spectra, so on and so forth. In case of thermal measurements, we are referring to temperature, flux, specific heat, thermal conductivity. Mechanical measurements, it would include position, velocity, acceleration, force, strain, stress, pressure, torque, so on and so forth. So these are the commonly measured quantities by different sensors. We do use many physical principles which account for most of these conversions between or transductions between one form of energy to the other. One of the very commonly used physical principles is the Ampere's law, which talks about the magnetic effects to a current carrying conductor. So when a current carrying conductor is placed in a magnetic field, it experiences a force. Very common example is the galvanometer, which is based on the principle of the Ampere's law. Again, we have the Curie-Weiss law, which talks about the the paramagnetic behavior being exhibited by some ferromagnetic materials at a certain range of temperature, which is otherwise known as the transition temperature. Or we can talk about Faraday's laws of induction, where a coil always resists a change in magnetic field by generating an opposite voltage or current when placed in such magnetic field. We could also talk about the physical principles behind photoconducting effect, which is quite commonly used to outlay some of the sensors and actuator principles. In this particular effect, the concern is about light strikes to a semiconductor surface, semiconductor material surface, which changes the resistance of the material, typically decreases, example in the case of a photoresistor. So therefore, there can be an intensity measurement performed of the incident light by looking at such delta R's or change in resistance of the material. So that's the photoconductive effect. How to choose the most appropriate sensor? So you base your choices on many factors. For example, principal consideration is again the environmental factors. These are the most important in choosing sensors, because the the sensors would have a life based on the operating conditions. For example, some of the commonly used operating conditions could be the temperature range over which the sensor needs to be used, or the effect of humidity, effect of corrosion, size, overrange protection, susceptibility to electromagnetic interferences. You could talk about power consumption, you could talk about self-test capabilities or ruggedness. These are all the environmentally assisted factors which would be the first choosing guidelines for what kind of sensor needs to be deployed. Sensors need to be somehow graded to some of these environmental conditions, where we can ensure that even though some of these fluctuate very rapidly, the sensor will still have its normal performance. There is also a set of factors about the economic viability or feasibility of the choice that you are making in terms of a sensor. It could be in terms of cost, availability, lifetime of the sensor. There are also characteristic based choices. For example, what sensitivity is needed by the sensor, what is the range across which it needs to operate, what is the stability in the what is the necessary stability for the output, how repeatable would be the sensor, or what is the linearity that the sensor must provide. Is this linearity in a certain range? For example, in temperature sensors, this is a very widely made observation that as the linearity proceeds across different ranges of temperatures, there may be a possibility that towards the higher range linearity may not maintain itself because of a changing physics with the concerned material which is in question. Okay. Again, you can choose sensors based on the errors that are permissible in a system where the sensors need to be integrated. You can also base it on the basis of response time. In gas sensors, this is a very critical domain information, that how much time would typically be needed for a sensor to respond and recondition itself for the next measurement. Again, the frequency response also happens to be a very important characteristic for choosing a sensor. So these are some of the criteria for choosing such sensors. The need for sensors are quite pervasive. They today, if you look at all around you, there are so many different aspects in which sensors are needed. Sensors are within human bodies, they are within all automotives, intelligent systems, airplanes, for example, cellular phones, radios, chemical plants, industrial plants. If you look at the domain, it's so vast that it's almost countless. There is a need for sensors at almost all steps to safeguard, to protect, to make sure that systems are within control. And typically we can call this or we can make this statement saying that without the use of such sensors, which actually is able to monitor and feed back the signal, there will be virtually no automation possible. So sensors do form a very, very important aspect of almost all mechatronic systems, intelligent systems, what we are discussing in this particular module. Let's look at some of the interesting sensors which are very commonly available, which are used mostly in day-to-day life. The first example that comes to our mind is motion sensors. You must be quite aware of such sensors in almost all engineering systems, which has relative motion between its components. So such a sensor would typically read the absolute or the relative position, or the angular or relative displacement, or even the proximity or sometimes the acceleration of moving parts. The principles of operations are manifold. For example, there can be magnetic motion sensors, there can be resistive sensors, capacitive sensors, inductive sensors, eddy current based, variety of other methodologies for doing sensing. Here are some examples. This is the very commonly used potentiometer which is represented through this wiper, which wipes on this lower stage, which is a resistive element. There is a motion associated, a forward motion associated with this shaft, across the shaft and seal bearing, shaft seal and bearing in the forward manner, okay, through this element right here, which forms a part of the circuit. So the idea is that if this wiper goes ahead with forward motion from this block shaft assembly, there is an inclusion of more amount of resistance, okay, as a function of motion. So as the resistance changes, we could see that motion is being executed. So if supposing a linear motion provider which is needed to be sensed is coupled to this system, which helps to propel the shaft in the forward direction along with the block, it will show up, if I connected this to a voltage divider circuit and assumed that motion gets executed, means resistive change is there. So in a very simple manner, you could look at the resistance per unit length and actually compute the velocity of motion of an object connected to this shaft right here, okay, by looking at what is the delta R as a function of time. So this is one of the very simple motion sensors. And the other very commonly used is this linear variable displacement transducer. We commonly call this as LVDT. So the LVDT, or the linear variable differential transformer, is based on actually a AC transformer with a primary coil and a secondary coil, as you can see here in this layout, and a core which is magnetic in nature and is capable of moving up and down. So the idea is that if the core moves in a bottom up manner and covers more of the secondary coil, there is a change in the output which is measured between the two secondary coils, as you can see here, okay, laid out here. So any small motion could be very sensitively detected through this particular mechanism. You can see that at x equal to 0, there is a certain output response which is there, which actually changes if x oscillates to either end of 0. So if it goes down, there is a signal, okay, with a changed phase. If there is a motion, bottom up, there is again a change in the output with a change in phase across the 0. So this is how a LVDT works. Another very critical motion sensor is the opto-isolator, which is again used to sense angular or relative displacement, relative angular displacement motion. So here you can see a sensor and a source of light which is being cleaved through a small blocker, and the idea here is that the blocker can either move in this direction, or a blocker could be some kind of a rotor which can actually chop the signals coming from the source to the sensor. Okay, so as the light signals get chopped off, you have certain response which will indicate, or which will basically try to account for the angular rotation of the linear motion. So that is how you can use various principles to sense motion. Another very important sensor which is used in most of the times in all motion, stress, or pressure measurements is the very popular strain gauge. Okay, so the strain gauge is typically used to measure deflection, stress, pressure, and a bunch of different mechanical parameters. The idea here is that it is a simple element, it is a simple resistor element whose resistance would change on different applied strains. So as this particular element is bent or deformed, it will change the overall resistance, and we can calibrate the extent of motion or the extent of deformation to, in terms of the applied strain, to the change in resistance for getting the strain induced in a real life system, looking at that calibration data for different runs. So typically the resistance change can be very commonly seen through a Wheatstone bridge. Such a bridge is used to measure small changes in the strain gauge. The idea here is that when this element is pasted on the top of this mechanical member, which is actually the specimen under the applied strain, the electrical signal coming out of this sensor would give you an idea of how much the mechanical member has compressed or expanded, okay, if there were an axial strain given to the member. So another very important sensor is temperature sensors, and one of the most common variety of temperature sensors is bimetallic strip. So the basic principle here is based on the temperature coefficient of expansion of metals particularly. In this particular case, there are two different metals, A and B, which has a different beta value, okay, where a change in temperature would definitely expand the length of a particular metal, starting with length at room temperature being L0 and the room temperature being T0 actually. So the idea is, if there are two different expansivities, thermal expansivities of the metals, and they are stuck together, the only way to ensure that these metals are still maintaining contact is if the metal assembly here or the metal stack here bends up or down, and such bending may lead to either de-switching, okay, or loss of contact, electrical breakdowns, so on and so forth. And it kind of gives you an idea of what is the temperature beyond which the electrical breakdown should happen. So typically all the fuses, the electrical fuses where short circuit executed has to be used as a call for circuit breakdown or ensure that there is no electric supply. This could be a very good alternative. In fact, towards the very beginning, these bimetallic strips were used for that purpose. Later on, of course, there had been other modes of electronics being introduced into the design, where there is a cutoff based on a certain gate voltage, etc., and it leads to the circuit to break, the electrical circuit to break. Another very useful temperature sensor is the resistance temperature device, RTD, which basically again works on the principle of the change of resistance based on temperature. So here in this particular case, the metal is such, either it's a metal which is actually which shows a linear change, or a material where there is an exponential change of resistance with respect to a certain temperature over and above the room temperature. So the idea is that as the temperature of a certain small region is taken over this value T0, there is going to be a delta R, where delta R is known by R minus R0, and this is a very important parameter to monitor, once calibrated and all, what is the temperature at any given point of time, okay, of particular devices where these RTDs are mounted. There are a variety of other temperature sensors. One of the common sensors are thermistor, for example, which is a thermal resistor. Here with change in temperature there would be a change in resistance, where this Eg is basically the band gap, particularly in zinc sulfide and other semiconducting materials, forming a certain kind of thermal resistors or thermistors. So it basically depends on the temperature state that the electrons are in and the band gap energy which is there between the valence and conduction bands, the material. So other form of temperature sensors are thermocouples based on Seebeck effect. They transform either a temperature difference to a voltage difference. So these are some of the commonplace temperature sensors available. There are also capacitance transducers which are used in a lot of different applications as sensors. The basic principle is a change of any of these parameters, on the basis of which capacitance between two plates could possibly get changed. Either there is a change in the dielectric constant of the medium, there is a change in the distance between two plates of a capacitor, or an overlap area change, so on and so forth. The permittivity of free space cannot change, so this is only constant in the capacitance parameter. One such example could be some kind of a level sensor, liquid level sensor, where there is a capacitance with this air escape hole given for bleeding out the air which is trapped in between, and a tube across which two metal conductors are placed, okay, on both sides. The idea is that as the tube, as this whole assembly is immersed into a tank, let's say a fuel tank sensor, for example, this petrol or diesel depending on the type of vehicle, and when the liquid goes into this tube, it changes the dielectric constant, and therefore there is a change in the capacitive response coming between these two plates, plate P1 and P2, shown by the two open areas. So it could gauge the level up to which fuel is in a particular tank, which is otherwise which cannot be gauged because it's completely closed with only entry for fuel and bleeding out air. So the following variations can be utilized to make capacitance based sensors. You could change distance between parallel electrodes, could change possibly the overlapping area of parallel electrodes, again change the dielectric constant, okay, and that could give you change in capacitance, response in capacitance. Some of the widely utilized capacitive sensors are, for example, accelerometers. These are used to measure acceleration along one or more axes and are relatively insensitive to orthogonal directions. Applications could be in a variety of motion and vibration studies. You could actually measure motion, measure vibrations, blast, impact, shock waves, so on and so forth. And the basic principle is again a vibrating mass with a base which actually transfers the vibrations from the source to this accelerometer. And the transfer happens through a parallel combination of a linear spring and a damper, and based on the motion of the mass, we are not actually getting into the mathematical description, which is actually more like a UG level problem. Here it is an overview about how these sensors can be utilized into various products. Okay, so there is a change of capacitance because of overlap area between the mass on one side and maybe a position sensor on the other side, which will cause again a capacitive signal. Now the signal is all well calibrated in advance, so you could actually measure vibrations, for example, using such an orientation. There could be other complex forms of accelerometers. Accelerometers could be in electromechanical devices which could measure static forces like gravity pulling at an object lying at a table, or dynamic forces caused by motion or vibration. How they work, in one of the types of accelerometers there is the seismic mass. I think I just mentioned this earlier. Is connected to an object undergoing acceleration through a spring and damper. The other, there is a mass which sits on a piezo crystal. The piezo crystal is stressed by acceleration forces and it produces in turn a voltage output. So the basic principle here is, in the motion analysis of the mass spring system, what is the change in the frequency as a function of the applied load, for example, or through which you could actually get what is the magnitude of the load, and also get a temporal response from the particular motion causing element. Now, there are various applications to which accelerometers could be used. A lot of it goes into automotives. Typically, accelerometers are used to monitor the vehicle tilt, roll, skid, impact, vibration, and is used to open close many safety devices. For example, stability control, anti-lock braking systems, airbags. They're all initiated, actuated through accelerometers. And the purpose of all this is to give a comfortable ride feeling to the passenger. There's a lot of use that accelerometers find in aerospace. Accelerometers find use in inertial navigation, smart munitions, unmanned vehicles. There are a variety of other areas where these can be deployed and applied. So you have sports and gaming, personal electronics, security, industrial usages, robots. So they in various capacities utilize some of these accelerometer sensors. Sensors can also be utilized for various light devices or devices which get actuated with light. For example, cameras or infrared detectors. Here the sensor is composed of a photoconductor, mostly something which gets actuated in terms of its conductivity through exposure to light. There could be a photoresistor or a photodiode or a phototransistor. All of these are amenable. This is a photodiode, for example. There is a light signal which is coming here. This is H nu, and it changes the the electrical band gap, and so there is a change in the resistance of the device based on such an exposure to a certain light. And so if you could calibrate the exact change in resistance with respect to the light that is falling in terms of its intensity or maybe wavelength, that could give us a very good idea about what is the level at which the radiation is taking place. and can be used very well as light sensors. Another class of optical sensors could be photoresistors. These are light sensitive variable resistors. The material where the resistance depends on the intensity of light incident upon it. For example, under dark conditions, the resistance typically would be very high. Okay, this is called typically the dark resistance, almost mega ohm range. And as the intensity increases, the radiation increases, the resistance is lowered almost to a few hundred ohms. So there is a large operation range of these photoresistors. They have excellent response time. It takes about a few milliseconds to lower the resistance, at least comparing some of the mechanical devices. This is on a much faster scale that you can have such changes. So photoresistors exhibit nonlinear characteristics for incident optical illumination. So therefore it's a log scale which could happen to have a linear characteristic, as you can see in the plot right here. These are how some real devices look like, photoresistor devices. So these are another class of light sensors. There are sensing, is carried out for magnetic fields. A variety of applications exist for magnetic field sensors in power steering, security, current measurements, transmission lines, so on and so forth. So the basic principle is the Hall effect, which is the production of a potential difference across an electrical conductor. In this case, you can see that there are a group of positive and negative charge layers which are accumulating on both sides, and this happens particularly when a magnetic field is applied to a direction that is perpendicular to the flow of current. So if there were a current flowing in a certain direction in which there is a perpendicular magnetic field, there would be a voltage developed in both ends of the conductor, which is otherwise known as a Hall voltage. So with this measurement, we could actually calculate the impact that the B field or the magnetic field has. The voltage is higher than the B is higher, and so on and so forth. And so magnetic field sensing can be done using such Hall sensor strategies. This is another very commonly available ultrasonic sensor. So these are used for position measurements. Basically the idea here is that the device emits sound waves in the ultrasonic range 2 to 13 megahertz, and whatever portion of it is reflected back and received is used for finding out the proximity of an object through which it is reflected. And so it's used in a variety of applications like the sonar, the sound navigation and ranging, very commonly used in naval applications, or even in the ship navigation industry. You can also use it as a radio detection and ranging radar application. Only difference in this case is that the same principles are deployed through electromagnetic waves rather than sound waves. So the basic principle in such sensors is that the distance of an object could be gauged by an assumption that the waves would get reflected back and come back in time and be received at the source emitting the particular signal. The signals could change in different frequencies or different types or natures. So I would now like to just change gears a little bit and go into a direction. You have had a basic idea about mechatronics, about interface building, about some sensors which are used for a day-to-day purpose. Now I think we can look into the basic principles of how intelligent products are designed, and maybe just give you an illustration through some examples of certain intelligent product designs activities which have happened world over, just to give you an idea of how you could make a product intelligent. So the basic principle that is used in such design experience is that you spend more time developing the intelligence rather than the interface. Okay, so this is something that you must get a priori, that you cannot just confuse the customer with too much of electronics, too much of interface, too much of control, but develop something intelligently so that the customer is happy that this feature is very, very useful to a certain product that he or she is using. So don't build what happens offline, build something that can't happen offline. Okay, so typically these are all real-time products. I'll show you some examples, some case studies done earlier through some companies. There was a case where IDEOs launched a smartphone which would assist women for their exercise schedules and give them instructions so that they could perform, outperform, so on and so forth. So in similar manner, okay, so everything which is real time works out well if you're talking about intelligent products. Don't think in sessions, think in relationships. Don't abstract success to digital metrics. If you think something, overlay your service onto existing platforms rather than making new platforms which are more complex in nature and not user friendly and so on and so forth. And do not wait to be asked that can you do this. Okay, if you have something in your mind where you think that the overall intelligence level of a product or a performance can go up, just outright apply to a product which is existing in some nature. Building up an interface can come later on. Okay, so you could also adjust the service based on the customer's behavior and context. So let's look at some examples. For example, I was just talking a few minutes back about this, the IDEOs tie up with a Japanese electronics manufacturer who designed a device and smartphone app that captured a woman's activities throughout the day. Okay, and the idea was to generate thoughtful, actionable insight about her individual fitness choices. This is an example. An SMS coming out of the device says, "Great power walk. You've already burned 102 calories. Can you burn 120 before the walk's over?" So this is an example of a real-time interacting system on the ordinary cell phone, which can only be possible through some kind of a web app. But the utility that it has is that once this app is on, it can keep on giving you secret text messages, okay, to the participant during the workout session, which can enable to perform and sometimes perform to the expectation of the target set for the particular day. So this is kind of a real example of how intelligence can be delved into an existing platform or a product. Another very good example is how to make a cup of tea using a voice command. So the key features that you should have are, you should be able to remotely assist the boiling process in a kettle from anywhere. So use the Smarter app to control your iKettle from wherever you are. So you could actually schedule for boiling of the water just before you hit the office or just before you supposing coming home, so at a distance mode through a small GPS system, probably a GSM system, probably you could use the cell phone network to send a voice command or maybe even a normal command, so that a switch on this kettle gets executed and the boiling starts, and by the time you're home or by the time you're at office, you get hot water. So these kind of small intelligent thinking processes which could be integrated to the normal products in existence, okay, could actually make products become intelligent. So let's say we wanted to interface to open a car door and get a signal when you're carrying the car key or not carrying the car key. So the best interface is no interface. We do not always need an app for that. Let's say one example could be the opening the car door. So the solution one could be that you have a screen based thinking process to make an app where you walk up to a car, pull out the smartphone, wake up the phone, unlock the phone, exist the last opened app, exist my the last opened group, swipe through the sea of icons searching the app, tap the app icon, wait for the app to load and try to find the unlock action, make a guess with the menu and tap control and tap the unlock button and then slide the slider to unlock and physically open the car. door. So this is not the goal. Okay, so this is like a very complex solution which is in there. If you could eliminate the graphical interface into question, where you're doing all these file scannings etc. to access an app through which you can open a door, we only need 2 steps in the whole process which are of use to the user or the driver. So one is that the driver approaches the car and then the driver opens the car door. So one approach could be that, and in fact this is a real approach, real solution given by Siemens. It was used by Mercedes-Benz in one of the models that they have. So when you grab the car door handle, okay, a logical part of opening the car door is basically grabbing the car door handle. The car automatically sends out a very low frequency radio signal to see if your keys are in close proximity. Your keys do have that remote assistance button, which is like a small controller which is there in your key itself. Say in your key or in your purse, if in your pocket or in your purse, if there is the existence of the key, you're carrying the key or the rightful owner, the door automatically opens. Okay, so this is like building from a web of different applications and accessing the right area, trying to open up the car door through the mobile phone that a person is carrying, to a very, very simple situation where the car makes a signal to gauge whether the key, which is having a small controller, is with the owner and the owner is the rightful owner, and if the frequency matches, the door automatically opens. So this is how intelligent thinking has to be embedded within the design process. So I think I am able to, in whatever time we had, this is of course the last module of this particular course, create some kind of a stimuli in all of you that to use whatever you have learned in the mechatronics, in the sensing, in the actuation, in the electronic control and interface building area to the minimum possible extent to make a simple and easy solution for a person, and that's what intelligent product design is all about. I think I'll close this module in the interest of time, and thank you very much for patiently being with me through all this. We have had a wonderful time going through different illustrations from principles of computer-aided design to how you could do intelligent rapid prototyping or manufacturing, some of the very basic concepts into realizing a design, and then delving into the MEMS area, and then finally into this mechatronics and controls, and then building up intelligent products through all this. So I hope you had a reasonably good time staying with this particular course. Thank you very much again, and I will close this course now. Thank you very much.